Hello and welcome to this Edexcel Further Maths Statistics 1 video looking at the mean and variance of the geometric distribution. This slide just reminds you of the probability function for the geometric distribution, and remember the only parameter involved is p, the constant probability of a success at any one trial. The random variable involved is the number of independent trials necessary before the first failure occurs, and the first possible outcome for that random variable is 1. For the geometric distribution, the population mean mu, or the expected value for x, Ex, equals 1 over p, the parameter. There are different ways of deriving the mean for the geometric distribution, and we will look at a different way in the section addressing probability generating functions. But this video is going to look at a proof by exploring the definition of an expected value, which is the sum of x, the outcome, multiplied by the probability of obtaining that outcome. And for a geometric distribution, the first value that is possible for x equals 1, but theoretically there's an infinite number of possible outcomes for x. So we're summing from x equals 1 to infinity, and we are summing x multiplied by the probability of obtaining x. The trick, if you like, to make this much easier than it would be otherwise is to let q equal 1 minus p, and I think you've probably been quite familiar with that idea from the binomial distribution. And if you think about substituting q equals 1 minus p into our expression, that would actually give me p equals 1 minus q. So, and I'm going to be lazy and not put the summations on, it would be the sum of x multiplied by p, which is 1 minus q, multiplied by 1 minus p, which is q to the power x minus 1. And having obtained our expression in this form here, we can then multiply out. And if we multiply here, x multiplies 1, x multiplies q, we would have x multiplied by the q to the power x minus 1, subtract x multiplied by q to the power x, and q to the power x comes from q multiplied by q to the power x minus 1. So you may like to pause and just check that you're quite comfortable with this line here. So the next clever strategy or trick that's going to be involved in this proof is to change the limits on the first part of our expression here for the expected value for x. And we are going to change limits, and you'll see why this is useful on the next slide, so that we are summing from x is 0 to x is infinity. And what we are doing is substituting x plus 1 for x, because when x is 0, x plus 1 is 1. So again, you might want to convince yourself about changing limits by pausing the video and just having a moment to look at that. And if we have a look at the a first summation here, when x equals 0, the first term there would be 0 plus 1 multiplied by q to the 0, and then we would have the summation, that the rest of the terms in that summation, which would go from x is 1, the next term up to infinity, of x plus 1 multiplied by q to the x, and we still have the second part of the expression, which is the summation of x multiplied by q to the power x. And 0 plus 1 is 1, q to the power 0 is 1, so this term gives me 1, and then I have two summations that you may see have something in common. I have x plus 1 q to the x So we saw on the previous slide how the first term when x is 0 of the first summation here gives us 1, and then we're left with the rest of the terms to be summed for that series starting from x equals 1. And we still have the second term in our expression for the expected value, which is the summation of x multiplied by q to the x. And if we look at the second summation there, we can write that, and I will put the annotations in this time, we can write that as the sum of x multiplied by q to the x, which is looking at that product, plus the sum from x is 1 to infinity of q to the x, which is looking at that product, and then we still have to subtract the summation from x is 1 to infinity of x q to the x. And if you look at that expression there, hopefully you can see that these terms actually cancel out. And once those terms were cancelled out, we're simply left with 1 plus sigma x equals 1 to infinity q to the power x, and that now is a very simple summation. It's a geometric series. The sum to infinity of a geometric series is a divided by 1 minus r. Clearly for this series the first term when x is 1 is going to be q to the 1, and the common ratio is q because we are increasing the power of q each time. So a over 1 minus r simply gives us q over 1 minus q. And we have then 1 plus q over 1 minus q, and if we put that all over a common factor, we will have 1 minus q plus q, which gives us 1 over 1 minus q, or 1 over p for the mean or the expected value for the geometric distribution. The variance for the geometric distribution is defined as 1 minus p over p squared, and I will leave that proof for you to explore as an exercise. There are very many statistics books where you can find that proof. Fortunately, in terms of the formula book, you are given the expressions for the mean and the variance for the geometric distribution, as well as being given the probability function. So those are not expressions that you need to learn, but you may need to know how to derive them, certainly the mean. And the other method I talked about using generating functions is going to involve this function here, but at the moment we haven't explored that. But I think it's very useful to know that you do have that information in the formula book. Well, that's the end of this video. The next video will look at using the mean and variance for the geometric distribution.